Hello everyone, Dr. Young here, and we are going to take a further look into these amines. We're took a closer look at their acidity, basicity, and nucleophilicity. Right, and I mentioned before in the previous video that amines are everywhere, right? They have a wide variety of physical properties and chemical properties, and so we're going to take a look at some of the background stuff we need to know about how these behave in aqueous solutions and how they're going to react for us as nucleophiles. So first of all, their acidity, right? We've already done examples of ranking acids and everything, but I thought it wouldn't hurt to just throw this out there and give you some pKa's. So I wanted to rank these by acidity, and I took a look at all of these. I'm going to go ahead and draw the conjugates because most of these are neutral except for the ammonium over here on the second from the right. And so if I take a look at this one, right, I'm going to lose that H, right, if this acts as an acid. I won't draw the H plus for all of them, but I will for some of them here. And for this one, right, we'll have an NH minus. I should put all my lone pairs. The aniline, right, we'll remove its hydrogen. For this one, for the ammonium, that means if I lose a hydrogen from this, that means I'm just going back to a neutral amine. And then from my butane here, right, that would mean having a carbon that has a lone pair on it now and is negative. So here would be all the conjugate bases, right? I'm kind of comparing those to get a sense of the stability of things. Now, the big key thing for amines, right, is that nitrogen is more electronegative than carbon, but less electronegative than oxygen. So the stability of anions that are nitrogen-based is somewhere between the two of those, right? So if I look at this right off the bat, definitely I see that my neutral amine here, my propylamine here, is going to be the most stable because it's not even charged. Right, should be the most stable because it's neutral. So I'm going to go ahead and give that my number 1. That should be the most acidic. Because it's just going to go from something charged to being something neutral. That's generally favorable in terms of stability. Now, if I take a look at these, the rest of these, right, I've got a negative carbon. Oh, sorry, I'll start from the left. I've got a negative O, a negative N, a negative N, and a negative carbon. So right off the bat, I should see that my negative carbon should be the least stable. Right, this is going to be the worst acid because it's going to form a carb anion, which is going to be the least stable, highest energy one. So that'll be my number 5. That'll be my worst, right? Because I don't want a negative on a carbon. Now I've got negative N's and O's here. And if I look at the negative N's and O's here, I see that my oxygen, right, should be more stable. So I'm going to go ahead and put that for the oxygen here, right? This should be my number 2, right? A negative oxygen, an oxoanion, so negative oxygen, is more stable than, right, a negative nitrogen. So that's why this is going to be my number 2. Right? I'd rather lose a hydrogen from an oxygen than a hydrogen from a nitrogen. So that leaves my second and third one here. I need to kind of rank them. Now, the big difference between these two, hopefully that you recognize, is that the aniline has resonance has stabilization, right? You can delocalize those electrons and draw resonance structures. I'm only going to draw 1 because I don't want to just waste time here. But write 1 resonance contributor for this. Would look like this. And then I draw 2 more if I wanted to keep going, move that lone pair around the ring. And that's going to help stabilize it, right? We know that delocalizing a charge, spreading a charge out, it stabilizes it. So I'll write that on here. So delocalization stabilizes the charge. Stabilizes the charge. Compared to over here where you have a localized anion. Right, your negative nitrogen, it's in one spot. Here you have the negative on the nitrogen, but it's delocalized a little bit under some carbons. Not that the negative carbons are great, but still you're spreading out some, so it's going to be a little bit better. So if I was going to rank these, definitely my ammonium salt was my number 1. The alcohol is going to be my number 2. My number 3 is going to be the aniline. My number 4 is going to be the propylamine, and then number 5 would be just the butane. Right? So we've done problems like this before. This is nothing really new, but I just wanted to doubly emphasize this. Also, I'll put some pKa's up here so you have a sense of things as far as the acidities go. You want to remember that as far as pKa's are concerned, alcohols have pKa's, depending on what's attached to them, of like 15, 16, maybe 17 or so. Amines, these are up around 35-ish. Anilines are around 30-ish. Ammoniums, these are more around like 10, 11, 12, somewhere in there. They're about 10-ish, give or take. And then, right, your just alkyl CH stuff, that's up around now 50, 55, somewhere in there. So really, really high. So if you did look up pKa's, you should get the same ordering here. All right, the ammonium is the most acidic. And then the alcohol, then the aniline, then the amine, then the alkane. Now we should also mention, though, that amines are weak bases. They're not strong bases, right? They're not hydroxide or anything, but they are weak bases. And we want to keep that in mind, right? So if we're talking about basicity, let me put some lone pairs on here. Basicity, if we're talking about picking up a hydrogen instead of donating a hydrogen like we did in the last one, I will have this molecule pick up an H, this molecule pick up an H. This one cannot, right? So I'm just going to put that from the very, very beginning. Even if I did draw an H plus here, right, to have it pick up an H plus, this second one, sorry, the second from the right one, this cannot pick up an H plus. Right, and that's because it has no lone pairs or pi electrons, right? It has no free electrons, it has no lone pairs, and therefore it is not a base. So if you have an ammonium salt, it's not basic at all. It cannot pick up another hydrogen. Right? It's not going to be a base. It cannot act as a base. Whereas these other ones can, right? I have a lone pair on this oxygen, can pick up that H. The lone pair from this nitrogen can pick up that H. Lone pair from that oxygen could pick up that H. And that'd give us a variety of different conjugates. So let's look at our first one where I have this propanol pick up an H plus. Add that H plus, now we have a positive on the oxygen. Here I have my nitrogen picking up an H plus. And then lastly, this oxygen right here now no longer has 3 lone pairs, it only has 2 because it used 2 of its electrons to give to that hydrogen, so now we get that alcohol. And so if you look at these 3, we should be able to rank these also here, right? Definitely the least basic one is the one I said cannot even be a base, right? It's not even a base. So that's going to be my number 4. It's least basic, or in other words, not at all basic. And as far as the most basic one, right, the one that's most likely to pick up an H plus, or the most stable picking up an H plus, would be our rightmost thing, right? The alkoxide becoming an alcohol. Definitely the best base. Best base because it formed a really, it's because for 2 reasons, right? It forms a very stable conjugate acid. And it was unstable to begin with, right? Remember that your good bases are very unstable anions. So it's also a really good base because it's an unstable anion. Right, of real high energy, right? So O minus, that was our cutoff, right? Remember for what a strong base is. O minus or less stable is a strong base. So that's going to be my number 1. Now, if I compare the first and second molecules over here on the left-hand side, I have a positive oxygen versus a positive nitrogen. And so if I'm comparing the stability of these two, right, I want to remember that oxygen's electronegative, more electronegative than nitrogen is. Or in other words, oxygen wants to be negative, not positive, right? It wants to be negative more than it wants to be positive. Versus nitrogen is less that, right? Nitrogen is less electronegative, or in other words, it's easier for it to be positive. So since, and I'll write this here, since nitrogen is less, let me do this, since nitrogen is less electronegative than oxygen, it is more stable as a cation than oxygen is, right? Positive oxygen, not great at all. Positive nitrogen, not so bad, not so bad. So because it's less electronegative, or in other words, I'll put in parentheses, another way to say this is that nitrogen is more electropositive. Than oxygen is, right? It's more electropositive, it's further to the left on the periodic table, and so it's more able to handle that positive charge on it. So that would give us then my number 2 should be the amine, and my number 3 would be the alcohol in terms of their basicities, right? So nitrogens can pick up H pluses. They are weak bases. In fact, they do pick up a little bit of H plus even if you just put them in water. There's an equilibrium there where they pick up some H pluses. So you do want, and we use them, right? We've had examples of using things like triethylamine or pyridine as bases, using them to kind of clean up those free protons that might be formed from some acid-forming reaction. So we know that amines are bases. In fact, let me just draw real quick since I mentioned them. Right, I mentioned that things like pyridine, which was this aromatic compound, right? Pyridine is often used as a weak base in some reactions, things like triethylamine. Triethylamine, which is abbreviated as TEA, right? So you have a nitrogen, right? Triethylamine often used as a base, for reactions like with SOCl2 or SWERN, something like that. So you do see them being used as weak bases. They're not going to do an E2 or anything like that, but they will pick up an H+. Now, the nucleophilicity of amines. We haven't really talked about them being nucleophiles too much. I know that I've at least shown them as being the type of nucleophile that would do a conjugate addition to an alpha-beta unsaturated system. But I haven't really talked about using them in regular SN2s yet, and it's for the reason that I'm about to lay out here. Working with amines takes a little bit more thought than just like other nucleophiles. So they are considered good nucleophiles. They will just add into something. They do SN2 reactions quite easily. And they do SN1s also, but SN2s. And like I said in the previous slide, right, they are weak bases. So they go in that category if you have your old ionic reactions flow chart where we had good nucleophiles, poor nucleophiles, strong base, weak base, hindered, unhindered bases. They go with the good nucleophile weak bases, which was mostly the like acetate and the halogens is what you had before, but you should add amines to that. So I'm going to draw these out, take a look at what happens if I take this propylamine and add methyl iodide. So I'm going to put my lone pair, well, let me draw this whole thing out. And methyl iodide. And I'll put my partial charges on things, right? Iodine maybe a slight negative. Nitrogen has a negative, positive on the hydrogens and the carbons that it's attached to. And so if you take a look at this, right, definitely the amine is the nucleophile because it's got a lone pair and it's partially negative. Iodine is not very electronegative. And so our nitrogen is going to be attracted to this carbon here, right, the methyl carbon that has a positive on here. And it's just going to do a good old SN2 type reaction. Nothing fancy, nothing new here. Just backside attack. And when we do that, what happens is that my nitrogen, it has the methyl on it now. It still has the two H's that were already on it. And then the iodine got a lone pair, so it became negative. But when the nitrogen gave those electrons away, it became positive, right? So we have a ammonium salt. Now, the thing with the ammonium salts is they're relatively stable-ish, and it kind of depends on the pH of the solution that you're in here. But what can happen is that the nitrogen, right, it's positive. It can become neutral if it just gives up one of its H's. And if it gives up one of its H's, then it becomes this amine, right, this methylpropylamine. So let me clean that up a little bit here. Then we made some HI. And I'm going to ignore that problem for now. We'll talk more about the fact that that HI would be picked up by another amine later, but I want to talk about a different issue right now. The issue that I want to talk about right now here is that, like, let's say you just reacted literally one of these methyl iodides, but I have one equivalent of methyl iodide, right? So I have equal molar amounts of these two. The problem here that we want to talk about is the difference in nucleophilicity between these two amines, right? If I look at this amine up here, the first amine that we started with, the propylamine has one alkyl group donating electrons to it. And remember that that one alkyl group, that weak electron donating group, is going to make the nitrogen a little bit more negative and therefore more nucleophilic. But if I look at the product that I just made, it still has that same propyl group on it, but now it has a methyl on it too. And so now this molecule here, this has two alkyl groups, right, which we said are electron donors, which means this is now a better nucleophile, right? It's more electron rich, it's a better nucleophile. So what happens if you're not careful is that this will now react with another methyl iodide because it's going to outcompete it. It's more nucleophilic, the reaction is going to be faster. And so it can react with another one of these, do another SN2 type reaction, and add a second methyl. And we get the same sort of thing where I have this ammonium salt, but these electrons can be taken back to the nitrogen to get the lone pair back, spit out another H+, which is going to give us this dimethyl propanamine. Right, then you have H+, I-. Sorry, I know organic chemists are not good at these side products. I just care about the organic thing. But the problem with this is now we have a tertiary amine, which has 3 electron donating groups on it. So now this is the best nucleophile mixed around in this solution. Right, so now this thing is going to outcompete any of the other amines that are in the solution because it's the most electron rich, it's the most nucleophilic one, and so it can then go attack one of these CH3Is. Same reaction, right? Backside attack, good old SN2. And what you're going to end up with here is a nitrogen that got methylated not once, not twice, but 3 times. And now that the only thing that's on this nitrogen are methyl groups, it can't just like lose an H, right? It doesn't have any more H's here. So you just stop at this ammonium salt. Right, and remember that ammonium just refers to a nitrogen that is positive, right? Ammonium is a positive nitrogen. So you stop at this ammonium salt, and what happens here is that this is a problem called exhaustive methylation. That if you try to just like methylate in the mean, it tends to you just add a whole bunch. It just kind of it's just like a runaway because every time you alkylate it, you methylate it, that product becomes more stable. It's kind of like with the Friedel-Crafts alkylation, if you remember that. Every time you alkylated an amine, or an aromatic ring, that aromatic ring became the better nucleophile. So then you kept on alkylating that same aromatic ring over and over and over again. It's the same idea here. So what we have to watch out for, and I'll put this right down here, what you have to watch out for is exhaustive methylation. Or exhaustive alkylation. don't know if you guys heard that. My son forgot to turn off his light. Anyways, you have to watch out for this exhaustive alkylation. Now, once these alkyl groups, you can imagine if they become bulkier, this methyl is as small as you can get, but if they're bulkier, this becomes less of an issue because as you add on another bulky group, it's harder to get to the amine, but you still want to be mindful of it. And so we have all of these different ways of making amines, and that's going to be a large part of this chapter. So I'm just going to show you, this next slide is going to be a little overwhelming, but I'm going to give this to you in basically every single little video that we do from here on out to kind of show you why we're doing these different reactions. So this is the table for how we're going to make some amines. This is by no means all of the types of amine forming reactions, but these are the ones that we're going to talk about the most, right? So we'll review the LAH reduction of an amide. We'll talk about how we can make primary, secondary, or tertiary amines. We have different limitations, different types of R groups that we can put on those. We're also going to do the LAH reduction of nitriles, something called the Gabriel synthesis, the Hofmann rearrangement, and reductive amination. And we'll do the Mannich reaction also. So, but what I'm going to put here, right, is you can see that depending on what type of amine you want to make, we have different strategies. So if I'm trying to make a primary amine, that's really hard to do what I did on the previous slide. If you just add like, oh, I want to have a butylamine, I'll just take ammonia and add a butyl chloride or something like that, butyl bromide. That's probably not going to give you the primary amine you want because you're going to polyalkylate it. You're going to end up getting the di, tri, or even tetraalkyl nitrogen compound. So we have all these different ways, for example, of making primary amines, right? We have 3 different strategies for making primary amines, and it kind of depends on what kind of group we want, right? So depending on what group you want to put on there, we have different methods. So that's what the future videos are going to be like. Hopefully you have a little better sense of just the general reactivity of amines and their physical properties and everything, where we find them in biological molecules. And so in our next videos, we're going to review real quickly that reduction of amides and reductions of nitriles and the types of amines that we can make with them. Anyways, happy studying. Good luck.